Assume a manufacturer of AI systems that are meant to perform some sort of autonomous operation in vehicles. The manufacturer would like to assess the acceptability of the AI operations by the vehicle passengers, and fine-tune the AI behavior to better suit the passengers' preferences. However, the AI system itself cannot be altered as it is operating in a dependable way. It is considered a black box. The teaching platform can seamlessly mediate between the passengers and the AI system, operating on its own isolated environment, and integrating with the AI system's interfaces, hence, performing only dependable operations from a list of presets. The manufacturer can use the teaching platform to A. Monitor and quantify the human preferences, and B. Learn how to tweak the AI system's performance, creating a closed control loop. To achieve that, the manufacturer needs to implement a teaching application that retrieves data from sensors, and then uses a deep learning model to quantify the stress that the humans are feeling. This quantified value is then passed on in another model, that considers it along with information about the current environment state to infer the option from the list of presets that will lead in the minimization of passenger stress. As the human passengers may have different tolerance levels, this last model must be adaptive and learn as it goes. As such, we refer to this model as the personalization model. Under normal circumstances, the more a personalization model is used, the faster it will converge to the needs of the passenger. The manufacturer decides to take advantage of this fact and use one personalization model to improve the other, by employing a federated learning concept. To do so, the manufacturer sets up an external service with which the local teaching application in every vehicle is communicating over 4G or 5G, or through a potential roadside communication infrastructure, over short-range communication channels. The objective of this communication is to share the local personalization models with the external service, which then aggregates them, generating a new model that integrates the knowledge encompassed in each one of them. The new model is then sent back to the teaching application instances in the various vehicles, and it is used to replace the local personalization models. To ensure that these data are protected as they are transmitted over a public link, they are encrypted and decrypted at each end of the communication channel. With this functionality, the teaching application is now extended to include both the local on-premise infrastructure, but also external, creating a continuum between the cloud and the near and far edge, that is, the roadside and on-premise resources respectively. We examine this scenario from a technical perspective with the intention to assess the ability of the teaching platform to deploy an application such as the one described. In what follows, we simulate the conditions and perform a set of actions that demonstrate the desired capacity of the platform. For the hardware board of the teaching platform, we use the IMX8 Quad Max from NXP, which embeds two ARM Cortex-M4 real-time microcontrollers, four ARM Cortex-A53 low-power cores, and two Cortex-A72 high-performance cores. This is furthermore complemented by two GPUs, making this architecture a viable choice for dealing with both the predictability requirements of dependable systems and the high-performance computing requirements of AI algorithms. We use this exact board and an x86-64 machine to set up two teaching application instances. We use Kala to emulate the driving conditions in the vehicle, as well as an AI system that essentially navigates the vehicle towards its destination. To minimize the passenger's stress, the two instances are switching between three driving profiles that the Kala AI navigation system is offering. The stress is measured with the help of an array of sensors from Shimmer that measure the electrodermal activity of the passenger. To further simulate the network conditions expected on the road, we use a network conditions emulator. Let's see what the manufacturer's developer needs to do to deploy the application. First, the developer starts with the selection of the needed microservices in the data workflow. These are the message broker, the sensor API, the stress and depersonalization models, the DP, a component called MTS that encrypts and decrypts model weights and sends and receives them to the external model aggregation service. Some of those are ready to be pulled from Docker Hub by just defining their name and the desired architecture, while some others need to be built. This is possible by using the templates that can be found in the teaching GitHub and extending them. There are specific templates and instructions for general-purpose components but also for deep learning models. To accommodate the requirement of dynamically creating data workflows, the teaching platform uses a message broker based on AMQP. All the component templates include a RabbitMQ client allowing them to publish or subscribe in a queue. They also internally expose a sort of listener interface that the developer can use to have their code produce or consume data automatically.
Let's assume that each of the two teaching platforms is running in the vehicles of each of two passengers, passenger 1 and 2. Passenger 1 is using the teaching app for as long as it is needed for the personalization model to be trained. The stress model has already detected cases where the passenger shows high stress levels, and the personalization model has correlated the high stress levels with contextual events, like sharp turns, bad weather, and high speed. For the sake of the experiment, we created datasets using human heart rate and electrodermal activity readings that we collected using the shimmer sensors and the IMX8 board. 2 humans were involved, 1 for each passenger. We then shifted the readings in a way that peak values are linked to the vehicle's angular velocity and speed in a different way for each passenger. In this way, we created 2 artificial passenger profiles that the AI models managed to approximate. Notice how the teaching app shifts to driving modes in a way to reduce passengers' one's stress levels. It shifts to the less aggressive driving mode in turns and to the more aggressive mode in straights. That is, driving modes 0 and 2 respectively. Passenger 2 has just started using the teaching app. The personalization model has no data to correlate contextual events with high stress levels, and it is stuck in mode 2. The vehicle is moving as fast as it is allowed, and the passenger's stress levels peak frequently. The teaching platform is then pushing both personalization models to the aggregation cloud service, where the untrained model from passenger 2 is essentially replaced by the trained model from passenger 1. The model is then sent back to the teaching platform of passenger 2 and replaces the old one. The result is the starting of the operation of the personalization model in a way that is more tailored to the preferences of passenger 2.